Okay, so thank you very much, Dimitri, for being here today. A short introduction. So Professor Dimitri Nakassis is an archaeologist and classicist at the University of Colorado Boulder. He specializes in studying early Greek communities, particularly Mycenaean societies of late Bronze Age Greece. Professor Nakassis received his degrees from the University of Michigan and the University of Texas at Austin, and he has taught at various institutions, including Trinity University, Florida State University, and the University of Toronto. He has been recognized as a college professor of distinction by the University of Colorado Boulder, and he holds one of the most prestigious fellowships in the field, the MacArthur Foundation Fellowship. Professor Nakassis' research focuses on re-examining Mycenaean society's hierarchy and dynamics through the investigation of individuals named in linear B tablets. He is co-director of the Western Argolid Regional Project, a diachronic archaeological survey in southern Greece, and co-director of the Pylos Tablets Digital Project, which involves the digital documentation of all the administrative documents from the Palace of Nestor at Pylos. He also works on topics such as Homer, Hesiod, Greek religion and history, archaeological survey, linear A, and the economy of the Mycenaean world. So, the floor is yours.
Great, thank you, Despina, for the invitation to talk to you guys today. I'm sorry I can't be there in person. It would have been really great to do it that way, but sorry, let me try to share my screen and so I can get going. Does that look okay to everybody?
Yes.
Okay. Okay, sorry, I'm just arranging my screen over here. So yeah, I might as well get into it. I always underestimate how long it's going to take me to talk about these things, so I should probably get going. Basically, what I thought I would do is start with a brief introduction to Linear B, and then hopefully brief introduction to Linear B, and then talk about some new approaches that are united by a kind of technological use of technology. I actually wrote, there's a new Cambridge companion for the study of Aegean scripts that's being edited by Jörg Weilhartner, and I contributed the paper about new directions or something like that. So I'm sort of cribbing off of that, but I'll focus more on stuff that I'm actively involved in myself or most familiar with, since hopefully, I mean, presumably I have more to contribute about stuff that I actually know something about. I guess normally the way this works is I talk for a bit and then there are questions afterwards, but if there are things that I say that don't make sense to you, please go ahead and, I don't know, find a way to ask the question as I go. I'll try to stop as I get to different sections, just to yeah, to give you the opportunity to ask questions if things didn't make sense. And then I guess maybe we can talk more questions that are more advanced. We can deal with at the end, if that's okay with everybody. So okay, so what's Linear B? Linear B is a script that was used to write Mycenaean Greek. So sometimes people will talk about Linear B as if it's a language. It's not a language, it's a script. And it's important, I think, to differentiate between languages and scripts because they're entirely different things, right? So Greek, for example, is typically written with the Greek alphabet, but when I was an undergrad, it was often very difficult to get Greek fonts to work on computers, and so Greeks would sometimes just write in Latin, right? Turkish used to be written with the Arabic script. Now it's written with the Latin script. So language and script are connected, but not necessarily so. And Linear B is typically described as a syllabic script, and that's because the core of the script, if you like, is a syllabary. That is to say, 89 or so syllabograms. That is to say, signs that represent syllables. So these are either pure vowels or consonant or consonants plus vowels. So a, e, I, o, u, ka, ke, ki, ko, ku, ma, me, mi, mo, mu, pa, pe, pi, po, pu, right? Those are values of linear B syllabograms. And syllabograms are used to write names and words and verbs and adjectives and all kinds of stuff. The script also uses a lot of logograms. So logograms are signs that represent words, or better yet, commodities. So logograms will be used to indicate men and women. They'll be used to indicate that are not commodified, but like where the scribe is trying to describe a group of men or a group of women. They can be used to describe agricultural products. So here, for example, this tablet here on the left, this is a logogram here. This is wine. This is a syllabogram that's used as a logogram. These are figs. Yeah. Here are men. So these are men, these are men, these are men, these are men. And then there are numerals. And linear B uses a decimal system for its numerology. So a dash here is 10. These ticks are ones. So 4 units of figs, 10 units of wine. Right. Okay. And so it's kind of, you can think of it as a kind of mixed system if you want. English can also use a mixed system. So this is my example of a mixed system English language sentence where we're using Latin alphabet to write IOU. We have a $sign, which is kind of the closest thing you get to a logogram in English. And 5, which is an Arabic numeral, right? So this kind of mixed system is not totally foreign to us. Although one thing that's worth noting about the logograms is that the logograms are not them, unlike the $sign here, logograms do not participate in grammar. You wouldn't use, so far as we know, you don't use logograms in linear B in a sentence, like as the direct object of a verb or something like that. The logograms are basically there as placeholders to indicate what is being counted. Okay. This is the tablet I always use. It's a terrible image, I'm sorry. I guess that's also useful for what I'm arguing here. So this is a tablet from Knossos that I always show when I'm teaching linear B. And usually what I ask is there anything you guys recognize? Does anyone recognize anything on this tablet?
Horse.
Horse, good. Or horse's head. So we're talking about this thing here. Let me see, how can I make this? Can I do it this way? Yeah.
So Dr. Dickinson is not participating because he says he will be sitting. So that
So there's the horse's head. Yeah.
It's bigger, I know, and no, it's a corselet. Corselet and a chariot.
Yeah, corselet here. Exactly. And chariot here. People often say fish for this one, for the chariot. Because I think they see the horse and then they think, oh, their minds go to animals. But this is a chariot. Yeah, so you can see here's the wheel in profile, and then here's the carriage of the chariot also in profile, and then the yoke has been twisted so that you can see it from above. Yeah, this looks like kind of a strapless dress to me, but it's a set of armor. And then this is the man's name, to whom this material is being allocated, or maybe he already has it. So his name is Opirimnio, which is actually a perfectly good Greek name, Opilimnios. So OP in linear B is often, for those of you who know Greek, OP, epi are the same. So Mr. on the water, something like that, Mr. on the
On the harbor.
right. Mr. on the harbor, something like that. So this is typically most linear B scholars work with these transcriptions. So if I just want to look at a tablet and see what it says, the transcription is the easiest way to do that. And the syllabograms are rendered in lowercase Latin with dashes between them to indicate that, like, they're different, to separate the signs. And then logograms are indicated with capital abbreviated Latin. So tune for tunica, big for biga, equus for equi for equus. So and then you can see in the break here, it's harder, you can see it too on the photograph if you know it's there, this curved line, which is we know from other tablets the remains of a ze. So the syllabogram ze, which is being used as an abbreviation for a pair here, modern Greek zevgari, right, or zeugos in ancient Greek. So a pair of horses, right, not just one horse. Would have been easier just to write two, actually, but I don't know. It's kind of interesting. Now I think about it, would have been a lot easier just to do two than to do ze one, right? But okay, so we have a bunch of different document types in linear B. Mostly what we're dealing with are tablets, and there's basically 2 or 3 different types of tablets. There are page-shaped tablets, like the one on the left here, which are, yeah, unsurprisingly page-shaped. That is to say, they're taller than they are wide, and they are about the same size as a piece of, they can be about the same size as a piece of paper, A4, or for Americans, 8.5 by 11. There are leaf-shaped tablets, which are these long, skinny ones. So you can see that, and I tried to, these are roughly at the same scale. I tried to make them the same scale. So you can see the page-shaped tablets record a lot more information than the leaf-shaped ones. The leaf-shaped tablets are basically a single entry, whereas, this page-shaped tablet has, maybe 20 entries, something like that, 15 to 20 entries. And then there's some intermediate shapes that you could call card-shaped or something like that. This one down here is an example of a kind of intermediate shape. There are also inscribed ceilings, not a ton of them, but so ceilings are lumps of clay that have been impressed with a seal, and then sometimes they can be inscribed with linear B on 1, 2, or 3 faces. So here you can see a scribe has, this is from Pylos, a scribe has written the wine ideogram on top of the seal impression. So these are all clay, right? And these administrative types represent the huge majority of the inscriptions that we have. Yeah, at least I would say 95%, something like that. There are some other document types. I'm not going to talk about them today, but I guess you might as well know about them. The most common other document type are these inscribed stirrup jars. They're not inscribed. In fact, they're right. The inscription is painted, but that's what they're called, ISJs. So these are all, well, they seem to be, the vast majority of them certainly seems to be made in Crete, Central and Western Crete, but they're found all over the Southern Aegean, or They're found in Crete and on the Greek mainland, in a variety of different places. I'm not going to talk about them. They're not my thing really. There's also a very, 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 very small handful of non-clay based Linear B inscriptions. So here's a stone weight from Dimony and a bone seal from Medeon. But it is surprising in some ways that Linear B isn't, a lot of people notice that or comment on the fact that Linear B isn't used on a wide variety of media. The way that contemporary scripts are often used on a wide variety of media. The scripts from Crete are used on a wider variety of media, right? Cuneiform is used on a wider variety of media, and then the Greek alphabet, obviously, as well. Okay. So Linear B, how is it used? I've sort of hinted at this already. What we have are administrative and economic texts, for the most part. Certainly all the tablets and sealings are administrative and economic texts. We don't have anything legal like contracts or law codes. We don't have any literary texts like epics. We don't have religious texts. We don't have letters. We don't seem to have any school texts for that matter. A lot of literary texts in the cuneiform world are in fact school texts. So that's kind of interesting. The tablets that we have seem to be purely palatial. One could argue about this, but the consensus among Linear B scholars is that we're dealing with texts that are written by and for people who are working for or with the palace. So we don't seem to have any private texts, private archives. The Mycenaean might have some, but most people think that those have to do with palatial operations. And we don't have any texts associated with temples or other kinds of institutions like we do in the Near East. And all of these documents are temporary. And the next slide explains that in a little bit more detail. So as far as we can tell, the tablets are not going to be kept. The tablets that we have were not meant to be kept for extremely long periods of time, probably maximum a year or so. Although there's a new tablet from Ios Vasilios near Sparta, which talks about 2 years ago, propersi, in modern Greek. And it's basically the Mycenaean word for propersi. So normally in the tablets, they talk about next year, this year, last year, and that's kind of the maximum time frame that the tablets talk about. And now we've got this one tablet that talks about something that happened 2 years ago. All the tablets are preserved by destruction fires. So they are none of them are intentionally baked. They are all burnt to a crisp by some kind of destructive fire. So you need to have a fire destruction in particular, in order to have Linear B preserved. So you need certain kinds of archaeological situations in order to preserve Linear B tablets and to have them discovered by archaeologists. And all of the tablets that we have were discovered by archaeologists. So unlike the situation in the Near East, we don't have tablets that are being, illicitly excavated and sold on the market. So this is a chart that John Bennett drew and I redrew. So here you have the destruction horizon, and you can see that we have tablets that are composed on an annual basis. We have tablets that are composed on a monthly basis, and then we have these kind of contingent tablets. And the point John was trying to make with this chart is that annually, tablets that are composed on an annual basis are likely to be retained on an annual basis and are thus much more likely to be preserved archaeologically. Whereas contingent tablets seem to have been written sort of on an ad hoc basis and then perhaps discarded. So those are likely to be underrepresented, right? So these tablets have shelf lives effectively, and we're much more likely to get annually composed tablets, and that skews what we think Linear B is doing. So the next slide explains a little bit of what I mean by that. So what are the major areas recorded by Linear B? Taxation is a big one. Those tablets are composed on an annual basis. So we would, taxation is probably overrepresented. Land holding, I'll show you some land holding tablets in a second. Labor recruitment, the tablets are very interested in labor. The payments of rations or wages in staple goods, those tend to be composed on a monthly basis. Animal husbandry, they're very interested in that. Craft production of different types, especially textile production and metallurgy at Pylos. Palace inventories, not as common, but we get them. And then religious festivals and offerings. So basically what the tablets tell us about is society, economy, and religion, seen through a very specific point of view, which is the palace's point of view. That's what I'm interested in primarily, is what Linear B tells us about what people are doing. So, the kind of historical or sort of social import of Linear B. I'll show you maybe the coolest, I don't know, a cool Linear B tablet. This is the longest sentence in Linear B. Here, let me show it to you again here. So we're talking about these two lines on this. It's not exactly page shaped. It's a big card shaped tablet. This is the longest sentence in Linear B. Eritha, the priestess, has and claims to have an etonio. Could mean something like true benefit for the god. But the community, the Damo, says that she has leases of Kekemena land, so much seed. And then they measure the size of the plot, the size of Eritha's estate, effectively in terms of grain. So this is the logogram for wheat, probably. And you can see it's 3 units of wheat, and then there's a subunit T, and then there's 9 subunits. So it's 3.9 3.9 of the big units of wheat. And that's not actual wheat. What that is seed grain. So you can see it's described as toso pemo, so much seed. So how much seed is required to sow the plot is how you describe its size. So we have a juridical debate here. We have some kind of dispute between a kind of legal dispute between a priestess and the community. All of these lands that are described in these tablets are on community land. It's land that seems to belong to the community and is managed by the community. So Susan Lupak has written a lot about this, what's going on here. But basically, all of you know about as much as anybody knows, right? This is the debate. What is the legal status of the land? Is it an etonio, or is it Kekemena land? Kekemena land is what everybody in this tablet has. Etonio seems to be special in some way. Okay. So that's the sort of brief introduction to Linear B, which probably took me too long. Does anyone have any immediate questions that I can answer, things that don't make sense?
In the room, we are fine.
Okay.
In the chat, people can put their questions, and yeah.
Yeah, you can put questions in the chat.
But we are fine so far. Thank you.
Okay. I didn't talk too much about chronology and space and time too much, but basically Linear B is we're talking about mature late Bronze Age. So 1400 to 1200 something in that range. Okay, so what are some new approaches? I divided these in my article, and I thought it made sense to do that. Here is looking, touching, reading, and future prospects. These really are new approaches, at least they're new to Linear B. So everything I'm talking about here has basically been done in the last 10 to 15 years. In this respect, I think Aegean scripts is, the study of the Aegean scripts is we're behind our colleagues who work with cuneiform tablets and our colleagues who work with papyri, which are the kind of most similar subfields. So let's start with looking. Part of the problem with Linear B is that they don't always photograph very well. I mean, this is a cherry-picked example, obviously, but the mode of the manufacture, the fact that these are lightly incised clay tablets, the clay is often not of the greatest quality. We'll talk about that a little bit some more. The fact that they're preserved by a destructive event means that they're often not super well preserved. This tablet's annoying because it's got a very uneven and mottled surface. So in a situation like that, raking light is often the best way to read a tablet because these are lightly incised. But when you use raking light, so light that comes at an angle, it highlights certain things but obscures other things. The normal kind of solution to the problem of representing Linear B, the one that was developed pretty early on, was something like this. So this is from the Thebes tablets. These are tablets from the city of Thebes in Greece. So you have a black and white photograph with raking light, as you can see. The right side of the tablet's in shadow here. So light's coming left to right, which is good for highlighting verticals. And then you have a line drawing, 1-to-1, and then you have a transcription. The transcription is only possible once Linear B is deciphered. That happens in 1952. So prior to 1952, you don't get transcriptions, but then once it's deciphered, then you can get these transcriptions, right? So this is a reasonable solution, especially if your aim is to publish in a printed book and color printing is expensive, right? And it does a really good job of giving you a lot of information. But there are also problems. The main one being that it requires you to put a lot of trust in the editors because the photographs often aren't of a fantastic quality. I mean, this is pretty good. But as you saw with the Knossos tablet, sometimes the photographs are really terrible. And if the photographs aren't good enough to challenge the readings of the editors, then you're basically at the mercy of the editor, right? Because the drawing is an interpretation of what's on the tablet. And both the photographs and the drawings are representations that require some kind of editorial intervention, right? You take a photograph of something trying to highlight the things that you think are there and that are important. So anyway, here's an example of why it matters. So there's a tablet from Knossos. Again, you can see these terrible photographs. These are published photographs. And it has this word at the end here, this entry called, that is read as maka. You can see there are dots under the ka, and that's because that means that the editors aren't 100% sure that this is the correct reading. I'm getting the morning sun on my head. So this ka is a little bit weird because a ka should normally look like this. It should be a circle with a cross inside of it. And the cross should basically go to the edges of the circle, right? That's the normal way to write a ka, and that's why this ka has been dotted. This matters because on Thebes, the sign sequence Maka shows up a lot, right? Here it is, Maka in Thebes, and here's Maka at Knossos. And so when the Thebes tablets were excavated and published in the, I guess they're published 2001, they were excavated in the early 90s, I want to say. These are the tablets from Odos Pelopidou, Pelops Street. Not Pelops Street, right? Pelopidou, Pelopidis, is that the nominative? I don't know. Anyway, when these tablets were excavated, they were like, oh, Maka, right? Just like at Knossos. And what's interesting about the Maka at Knossos is that, actually, I'm going to go back, is that she, well, assuming it's feminine, Maka is on the same line as Diwe. You can see Diwe here. And Diwe is the dative of Zeus, right? So to Zeus, barley, 2 entries of barley, kind of weird. To Maka, an entry to barley. So Maka could be a deity. That's exciting, right? So there's a lot of debate. Is this Maka? Is it really Maka? Is Maka a deity? At Knossos, what do we do? For some reason, it became a big deal. And this Belgian scholar named Yves de Hoe went to Knossos, and he went to re-examine the tablet that had at Knossos that had Maka. And what he decided was it wasn't Maka. He decided it was Makwe. So here's how he draws the sign, and here's how he photographs the sign. But you can see his photograph is misleading in some ways. The light is coming from above here, right? You can see the shadow here. You can see the shadow here. And there you can sort of see the, right, this line that the editors drew here, you can sort of see it here, right? But you don't see it well because if you the light is basically lined up to run straight down that line, right? The light is coming from this direction. And so if you have a light source that runs down inside and not very deeply incised line, I mean, this could, who knows what this is exactly? It's hard to say. It's not going to show up very well. So I would say it's a little bit, it's not the greatest practice to do this, right? To argue, because what he argues in this article that Maka is not a thing. That this is Makwe, and therefore this tablet tells us nothing about Maka at Thebes. So there are problems with photography. And so when we started working on the Pylos material in 2013, me and Kevin Pluta, we decided to use something called reflectance transformation imaging, or RTI. And basically how this works is that you take, we usually take about 50, what do we do? 54 or so images of each inscribed surface. The camera doesn't move. The artifact doesn't move. So we're like, you can't touch the table. This is like one of our cardinal rules. The only thing that moves between each photograph is the light source, which in our case is a handheld flash. So you can see it here. So, and then you can see here some examples of a tablet where the light is moving between each photograph. And each photograph has a black reflective sphere in it, 1 or 2, usually 2. And the sphere records where the light is coming from. So you can sort of see here, I mean, you can see the shadows, but you can also see that each sphere has a white dot, and that's the flash being recorded. Sorry, so my brother or something is messaging me. Okay, so how does RTI work? The computer knows that each photograph is recording the same thing. It knows where the light is coming from because the light is recorded on the sphere. So here's a composite image that shows all of the sources of light, all of the directionalities of the flashes that we took on a single set of photographs. So you can see you're trying to get good coverage. So usually what we do is 9 times 6, 9 different horizontal positions and 6 different vertical positions. So the computer knows that the object is static. It knows that the light is coming from a specific direction, and therefore it knows how each pixel in the photograph responds to light. And it uses that information to calculate the surface normal. So the surface normal is this red arrow in each case. So the surface normal is the direction that any given pixel is facing, right? And it calculates the surface normal on the basis of, like, you know, how light responds to surfaces. And this has been known basically since, you know, the 18th century or 17th century or something like that. I'm going to put something to block this light so it's not in my eyes, which is what it is doing right now. I'll be right back. It's going to work. All right. Sort of working. Okay. So at this point, I was going to show you an actual RTI file. So I'll do that. Can you guys see the screen?
Yes,
You see the RTI file?
yes, the photograph.
Yeah, it's not a photograph. It's not exactly a photograph, but yeah. So here's an RTI file. You can see the two spheres, and so the RTI file allows you to manipulate the light, like I'm doing now, right? Can you see that?
Mm-hmm.
Yeah. Okay. This is at 15%, so we can zoom way in to there, 100%. So it looks like it's moving around, but it's not, right? The shadows are moving around. So sometimes when you first look at an RTI file, you think that things are moving, but if you fix your eye on an inclusion, like this inclusion here, for example, you can see that that's not a good example. You want something smaller, like this one here. You can see that it's not really moving around. It's just the shadows that are moving around. So this is the default rendering. You can also use different rendering modes, because basically for this program, for every pixel, it records color, but also the surface normal. So you can even do something like this, right? So this is a normals visualization. Basically what it does is each normal is recorded as a vector with a distance of 1. So a perfectly flat pixel would be 0, 0, 1, right? The vector is going straight up. And then what the program does is it just uses RGB, red, green, and blue. It just maps that onto those 3 numbers. So blue is basically flat, right? So this is just showing you in color what the surface normal is. It's actually a pretty good representation. You can read the tablet, right, pretty easily, using the color, the normals visualization. But you can do stuff like specular enhancement. So this is basically stripping out color and boosting the specularity of the tablet, so that it's basically black and white, but extremely glassy. This is good for tablets where color kind of impedes your interpretation. You just want to look at topography, right? And you can move the light around with specular enhancement. There's some stuff like typical kinds of enhancements that try to diffuse gain is a nice one that basically highlights edges so you can see the edges more clearly. So this is a kind of way to RTI is a way to, instead of having a single static image, which never shows you everything that you're interested in, you try to take a whole bunch of images, which show you pretty much everything you could be interested in, you hope. And then these can also be united into a single file, which allows users to play around with the light. So this is not, I don't think this is better than autopsy. I don't think it's better than sitting in front of the tablet in real life. But I think it's a pretty great substitute for autopsy, given that not everyone can just pop down to Athens and go to the National Museum and look at the tablets, right? And you know, cameras are getting really great. This was taken with a 50 megapixel camera, so you can see the resolution is really nice. It's also I also have a fancy lens, so that helps too. Yeah, I'm really happy with the quality of these images myself. And this is a pretty commonly used. You can also see here the spheres. You can see how the spheres react with the light. This is a pretty commonly used. Actually, the reason I know about this, the way I learned about this technique is that they use it at the University of Chicago to document the Persepolis Fortification Archive, which are tablets that are from Persepolis, they're from a fortification archive. They date to the reign of Xerxes, I think. Xerxes or Darius? I think it's Xerxes. So early 5th century BC. So this is a technique that's being used by other people who are interested in clay tablets, but it's also used for like medieval manuscripts and rock art and all kinds of stuff. Anything where you're interested in where the object is more or less flat, the artifact is more or less flat, and you're interested in the topography, the texture. So you can see rock art or medieval manuscripts, right? We're talking about very slight differences in the topography of the surface. Okay, so that's RTI. Also, 3D scanning is something that people have been doing. And you can create three-dimensional models in a bunch of different ways. This is structured light scanning. That's been the dominant way that people have documented linear B tablets or linear B inscriptions. But there are other methods. The other main one that's been used for linear B is photogrammetry. So structured light scanning, the way it works is that you have some kind of instrument. This is a Breichmann scanner that projects patterns of light onto a surface. And then you have cameras, you can see on either side of the projector, that record how the light is being distorted or deformed by the objects that are sitting on the platform. And then it calculates the geometry based on the way that the light deforms, basically by triangulating. And that's the same way that photogrammetry works, right? Photogrammetry, oops, wrong direction. Photogrammetry, what you're doing is you're taking a bunch of photographs of an artifact from a bunch of different directions. And then the computer then produces a 3D model through triangulation. This has become really popular in archaeology, generally speaking, because it doesn't require special equipment beyond a camera and a tripod and that kind of stuff. And it's extremely accurate. So both methods can produce accuracy, really good accuracy, down to 30 microns. That's 0.03 of a millimeter. So here you can see photogrammetry being done on a clay ceiling. I'll show you the model in a second. That's being done by an Italian team. And this is my friend Phil Saperstein has an article about small object photogrammetry. And here you can see he's photographing this bronze figurine. I forget where it's from. And here you can see how the program understands what's happening. So each of these blue cards or whatever represents a photograph, and the direction of the photograph onto the towards the object. So you're basically creating a kind of sphere of photographs around the object, so that the computer has tons and tons of points to create a three-dimensional model. Common points, right? The computer basically says, oh, these 2 points are the same, right? Okay, so I was going to show you this. So this is the website of this Inscribe project that's run by Silvia Ferrara and her colleagues. So all these, you can look at these models yourself. You can see they've got a bunch of models here of Cretan hieroglyphic linear A, which is the kind of parent script of linear B, and this other stuff, Rongo. So we'll look at linear A. Oh, and I'll look at, here's the nodule that you saw them photographing before. And so here's the model. So you can manipulate it yourself. Here's the 3D model. And you can do, oops, it's upside down now. Oops. Oh, come, what am I doing? Come back around. No. There. Okay, we'll do it like that. You can also do, you can manipulate the light as well, right? So you can do RTI. If you have a 3D model, then ipso facto, you know the surface normals, right? So you can have something like RTI embedded within a 3D model, right? Now you can turn it off and you can move it around and you can measure a length there. That's 5.51 millimeters. And you can see here from the metadata that this is a photogrammetric model, and they've used a Canon EOS 2000D with an EF 100 millimeter macro lens. I don't know, is that a good camera? 2000 EOS D? Let's see. I'm curious. Yeah, it's not full size. No, it's not what I would use. But anyway, that's fine. It's a really great model. You can also see they have tablets too. This is using this is structured light, right? VGER ScanRider 1.2 is a structured light scanner. So this is a different method. I think it is higher quality than this. I think that this has been, I imagine that this has been downsampled somewhat, so it doesn't take up a huge amount of space and our computers don't jam up trying to download all the data. But yeah, you can see, and you can also do the same thing with kind of RTI it, manipulate the light. And likewise, you can measure, right? You can say, what's the distance between that and that? 19 millimeters. Okay, so just doing a kind of quick comparison between RTI and 3D scanning. RTI is 2D plus. Sometimes people talk about it. It's not really three-dimensional. It's recording an object in 2 dimensions, and additionally, it's topography, right? So 2 plus or 2.5, sometimes people call it. Whereas 3D scanning is true 3-dimensional, right? It really records geometry, not just topography. RTI is easier to do than 3D scanning. Generally speaking, RTI is open source software, whereas 3D scanning tends to be mostly proprietary software. I think RTI, this is sort of me shooting from the hip here, but I kind of get my impression is that the photographs, the sort of raw photographs for RTI are more useful for 3D scanning. the photographs are often more about producing the model, right? They're most useful in the model. And then storage, this is something that I'm concerned about as someone who has a bunch of photographs for RTI. Basically, we're dealing with about 3.5 gigabytes per inscribed surface. With RTI, if you're using a 50 megapixel camera. For 3D scanning, it depends on your technique and resolution, but for photogrammetry, it's typically you need about twice as many photos to do photogrammetry than you do for RTI. And if you're focus stacking, then you need even more photographs than that. So both of these methods, if you use photogrammetry or RTI, you're producing a lot of photographs. And that raises concerns about, archiving and storage and long-term storage, right? What's going to happen to these photographs in 100 years? That kind of stuff. So that's basically looking. I'm running up on an hour, aren't I? Let me, looking is the main thing. I'll run through the other stuff more quickly. So this is touching. One of the things about linear B tablets that is maybe a little bit surprising is that the clays are strikingly different. And we were really, in a way, kind of shocked by the diversity of the clays that are being used. The fact that many of the clays have these pretty big inclusions on the writing surface, that's not something that we expected. And so we were interested in trying to understand the diversity of the clays, which we partly did through traditional means, but partly through fancy means. And the fancy means are X-ray fluorescence, or portable X-ray fluorescence, I guess. So this is a non-destructive technique that measures the elemental composition of a sample. So we have, on almost all the linear B tablets from Pylos, we have XRF readings. And what we can do then is cluster readings that are similar to each other in terms of their elemental composition. We can use that using statistical software. And what's interesting is that the readings, not always, there's a lot of noise in the readings, but sometimes they pattern pretty strikingly. So this is I'm working this up for publication. These tablets are all from the same sort of bureaucratic office, the AC series, and you can see they cluster by location. So all of the tablets that record toponyms in the southwestern part of the kingdom are in basically the same XRF cluster, 4 and 5. And then all of the ones from the northwest are in 8 and 17, and the one from the southeast part of the kingdom is in cluster 12. So it looks like the elemental composition of the tablets basically maps onto the location of the places that are referred to in the tablets, which is kind of amazing. The other thing is reading. So one thing that these new technologies allow for are these kind of hyper accurate, hyper detailed drawings that do a better job of communicating not just what the signs are, but exactly how they were incised. And this is important because we can identify individual tablet writers or scribes, if you want, based on the analysis of their handwriting. So these high-res drawings allow scholars to analyze the handwriting in great detail and communicate that to other scholars. So this is basically derived from RTI. This is post-RTI analysis. But I thought I'd show it to you because it's super cool and I think it's exciting. This drawing was done by Alessandro Greco, who's got a project where he's doing RTI and 3D scanning of tablets at Knossos. There's been some interesting work on paleography to kind of talk about this scribal stuff. So on the right, you see Esther Salgarella's paleographic database of linear A. On the left, you see Christina Skelton's phylogenetic systematics of the linear B scripts. Basically, what she did is phylogenetics is a technique used in biology to track evolutionary relationships, and she did the same thing with linear B signs. So she's trying to track the development of the Linear B script based on variations in sign forms to create a kind of family tree of Linear B. Okay. So that's that. There's a lot more to say about this, but I'm kind of trying to make sure we get to the end. There are a whole bunch of databases that have been produced in the last 10 years or so. So the Cambridge Linear B Research Archive, the Linear B Electronic Resources, that should be LIBER, not LIBET. Sorry, that's a typo. The corpus of Cypro-syllabic inscriptions in Inscriptiones Graecae is also online. And for a long time, we've had online the corpus of Minoan and Mycenaean seals in the Arachne database. So we've got this kind of flourishing of databases for Linear B and associated scripts. But probably the biggest and the most useful database in some ways is the Damos database. This is the database of Mycenaean at Oslo. So it allows users to browse and filter and search transcriptions and metadata. And you can perform sophisticated queries, and it also links to other databases. So if you're looking at a tablet and you want to look at an image of the tablet, and that image of the tablet is stored in one of the other databases, it'll link to that image. So this is probably your best, if you want to mess around and play around, Damos is probably your best first stop. Okay, so future prospects, obvious things I think that could be done in the near future. So one is fully digital editions based on open access digital data sets. This is something that Federico Aurora, who runs Damos, this is something that he thinks is really important. So Damos is not, one thing that about these databases is they're kind of first generation or second generation databases. They're still kind of operating by scraping data from books and turning them into digital data, as opposed to fully born digital editions of Linear B tablets. This is something that Federico thinks we should do for Pylos, for example. Digital corpora, right? It's still the case that Linear B scholarship is based on books, basically print media. But as we've seen, print media has to resort to some solutions to capture information that maybe we don't think are perfect. And then, machine learning. Can we use computers not just to display information, but to actually analyze large data sets and give us some kind of analytical purchase that we wouldn't have otherwise? This is basically there's been very little of this, just kind of scratching the surface. And partially maybe because we don't have digital corpora and digital editions, right? That machine learning works best, obviously, when you have digital data sets that can just be mined without much work. So there's still a lot of work to be done. We're still kind of at the beginning of these digital approaches to Linear B and the scripts that are associated with Linear B. Okay, I should stop there, I think.